Hello student, my name is Nimish Prabhakar. I am Assistant Professor at LJ Institute of Engineering and Technology in Instrumentation and Control Department. Welcome to Process, Dynamic and Control lecture series. In my previous lecture, I complete chapter number 3, Dynamic Behavior of Boiler. Now, in this lecture, we discuss about the remaining portion of the chapter number 1. So, in this lecture, we discuss the dynamic behavior of first order system and dynamic behavior of second order system. So, we all know the equation of first order system. That means we can represent first order system by using this general equation. So, this is the equation for the first order system is tau p is equals to dy by dt plus y is equals to kp into f of t. So, here f of t is represent the input of the system and y, or we can say in a time term y of t is represent the output of the system. Same as here tau p is represent the time constant of the process, and Kp is known as the steady state gain or the static gain of the process. So, now we also know the Laplace transform of the first order system. So, Laplace transform of the first order system we can write as g of s is equals to y of s upon f of s is equals to Kp tau ps plus 1. So, this is the equation of the Laplace transform of the first order system. Now, we take step signal as a input. Now, to analyze the dynamic behavior of this first order system, we take as a input, that means we know the f of s is the input. So, we take as a input step signal. So, we know the characteristic of the step input. So, now f of t is the step signal we consider, and for the step signal we know the condition 0 when step signal value is the 0 when t is the less than 0, and a value a when the t is greater than or equals to, sorry, when the t is the greater than 0, not equals to, when the t is greater than 0. So, this is the represent the step input signal. Now, A is the represent the amplitude of that signal. So, now by putting the value, now to put the value, this is the, we know the in the t terms. So, now we have to convert into the Laplace transform. So, we know the Laplace transform of the step input is nothing but the f of s is equals to a by s. We know the Laplace transform of 1. So, 1 Laplace transform is the 1 by s. So, this is nothing but the a. So, here we can write the a by s. So, this is the Laplace transform of the f of t. Now, putting this value in this equation, we can write this equation number 2 as y of s is equals to f of s. So, here f of s is goes to the multiply. So, we can write the a kp upon s tau ps plus 1. Now, to take inverse Laplace transform of the equation number 3, we can write, that means we know we have to, if we have to take the inverse Laplace transform of the equation, this equation, so we cannot directly write the value. So, we have to take some assumption, and so we can write this equation as y of s is equals to a kp a by s plus b by tau ps plus 1. We know this is a procedure of the taking the Laplace transform of the taking the inverse Laplace transform of the any equation. So, now we can also write this equation as this tau ps is go in the multiply here, and this s is multiplied by here. So, we can write this equation as. Now, by substituting the value of y of s from the equation number 3, that means here we can write instead of the y of s akp 1 upon s tau ps plus 1 is equals to akp and this equation. Now here we can compare this equation. So by comparing this equation we can write as a tau ps plus 1 plus bs is equals to 1. So now to find the value of a and b, we can write this equation as, now to solve this equation, that means to get the value of the a and b, we consider s is equals to minus 1 upon tau p. That means here we consider s is equals to, so we can write from this equation s is equals to minus 1 upon tau p. So now substituting the value of s, this means this s in the equation number 5 in this equation. So we can write this equation as, so by substituting this value in this equation we get the b is equals to minus tau p, because here we put minus 1 upon tau p, so the tau p is cut and minus 1 we get. So minus 1 plus 1, so here this term is the 0. So here we can write the b is equals to minus tau p. Now when we substituting the s is equals to 0 in this equation, so here we put the s is equals to 0. So at that time this term is 0, so we can get the value of a. So at that time we get the value of a is equals to 1. So now we get the value of a and b. So now substituting this value a and b in this equation, we get y of s is equals to akp, and instead of a here we write the a is equals to 1, and instead of b here we write the minus tau p. So minus is here, minus tau ps plus 1. We can also write this equation as 1 upon s minus this tau p is common, so tau p and denominator and here cut, so s plus 1 upon tau p. So we know the inverse Laplace transform of 1 upon s is nothing but the 1, and this is nothing but the e raised to minus at term. So we can write this equation as akp is a common, and this is the inverse Laplace transform of this, and this term inverse transform is the e raised to minus t upon tau p. So this is the inverse Laplace transform of the first order system. Now in this equation we consider the t is equals to 0. So that means here we put, instead of t value is 0, so 0 upon this is nothing but the e raised to 0, and we know the e raised to 0 is nothing but the 1. So 1 minus 1 is 0, so we get y of t is equals to 0. So when we put t is equals to 0 in this equation, we get the 0. That means this response is start from the here, from the 0, beginning value of the is the here, and now we put the t is equals to infinite value in this equation. So we get y of t is equals to akp. That means the maximum value of this response is akp. So here we put the maximum value akp. The response is start from here, and maximum value of response is here, 0. And now we plot the graph of the t versus y of t. That means at the y axis we put the y of t, and at the x axis we here we consider as a t. So now response is start at the t is equals to 0 from here, and maximum value of this response is akp. Now the behavior of the response to get, here we put tau is equals to minus, here in this equation we put the tau is equals to tau p. So instead of here we put the tau p, So at that time tau p is cut. So e raised to 1. So we know the value of e. So by putting that value, we get the y of t is equals to 0.632 akp. That means this is the 0.6332 value of the y of t. So here from this graph, the behavior we can see this is the behavior of the first order system as a progressive manner, and here it get the maximum value. So the transfer function y of t reach at the 63.2 value. That means here we can write this is a percentage 63.2 of its ultimate value when t is equals to tau p. That means at the t is equals to tau p, this y of t it reached at the 0.632 value. That means nothing but the 63.2 percentage of this akp value, maximum value. Now, so the time constant can be defined as the time required to reach y of t to reach at the 63.2 percentage of its ultimate value. That means this is the importance of time constant in any system. That means time constant is represent the value it's required to reach 63.2 percentage at its ultimate value. This ultimate value is nothing but the akp, and this y of t is represent the response of the system. So this is the importance of the time constant. By using time constant, we can know the response of the system. That means its behavior we get. So for further understanding, the speed of response is related to tau p. That means here we can say by using this phenomena we can say the speed of system or the response is related to tau p value. That means if tau p is smaller, that means here then faster will be response, because here the tau p value is small we consider. So at that time we get the faster response because it reach its value 0.63.2 percentage of the final value in that time. So tau p is represent the response of the system. That means the response of the system is faster or slower. We can know about by using the value of the tau p. So this is the different value. This is a table of for the different value of the t, and this is the response value. When we put t is equals to 0 in this equation, we get 0. When we put t is equals to tau p in this equation, so we get the 0.632 for the of the final value, and same we can put. So when we put the value 5 tau p, at that time we can reach almost 0.99. That means we can reach at that final value. So by using this table we can say to reach the final value or the ultimate value of the response, we have to write here the 5 tau p. Okay. Now we see the dynamic behavior of the second order system. So this is the equation of the second order system. So we know the here we can we can write the transfer function of the second order system as the g of s is equals to y of s upon f of s kp tau square s square 2 zeta tau s plus 1. We know this is the Laplace transform of the second order system. So here the tau is represent the natural period of the oscillation of the system, zeta is represent the damping factor, and kp is represent the steady state gain of the system. So here, to know the dynamic behavior of the second order system, that means the dynamic behavior of the second order system, it depends on the value of zeta. That means this value zeta, damping factor. If the zeta is greater than 0, if zeta is less than 0, and if zeta is equals to 0, then dynamic behavior of the second order system is changed. Now we understand by using graph. In the first one case, we consider that zeta is equals to 1. So at that time, the system is known as the critically damped system. And when case 2, when zeta is greater than 1, so at that time system is known as the overdamped system. See here, by using this graph, here we can see when the zeta value is equals to 1, this response is known as the critically damped system response. And when zeta is greater than 1, at that time we can see here this response is known as the overdamped response. So this is a representation of the zeta. And now when zeta is less than 1, the system is known as underdamped system. See here, this is the value of zeta less than 1. See 0.7, 0.4, 0.1. So here the damping factor is less than 1. So this response is known as underdamped response. See, this is a unstable system. Now from graphical representation we can conclude, that means for the second order system dynamic behavior, we can say from this graph, in the third one case the output is a damped sinusoidal signal. That means this is a sinusoidal signal, and the underdamped response is initially faster than the critically damped and overdamped response, which is characterized as sluggish. That means here we compare the underdamped response and overdamped response. So we can see here underdamped response is initially faster as compared to the overdamped response. See here, this is the overdamped response and this is the underdamped response. See, this is the underdamped response is initially faster compared to the overdamped response, and overdamped response which characterized as sluggish. That means here we can see this is a sluggishness of the overdamped response. Sluggish, that means nothing but we can say the delay or the response is slow as compared to this system. So here we can say this is also the overdamped response represent 1.5. So this is a sluggish response as compared to the underdamped response. Now we can also compare from this behavior. Although the underdamped response is initially faster and it reaches ultimate value quickly, that means it reach underdamped response is faster and it reach its ultimate value, that means is fast and quickly, it does not stay there, rather it start oscillating. We can see here it start oscillating. So this is the oscillation. In the overdamped system we cannot see the oscillation. Here the underdamped response is initially faster and it can reach its ultimate value faster, but it start oscillating. So we can say the underdamped system is the unstable system, and increasing in the zeta reduce the oscillation but also slow down the response. So to reduce this oscillation, that means the unstable system, we have to increase the value of the zeta. So when we increase the value of zeta, at that time this oscillation is reduced and we get the stable system. But we also saw the response of this system is reduced. So in other words we can say, if we increase the value of zeta, that means 0.2, 0.4 and 1, 1.5, So the response of this system is slower. So this is the dynamic behavior of the second order system.